Swayam Prabha. Digital India. Educated India.
Hello students, welcome back, and let us now discuss how thermodynamics defines the equilibrium state of a macroscopic system in terms of three variables and three variables only. For this purpose, I have chosen to work with 1 mole of an ideal gas, and this example is something that you have seen many times before during your high school days. But I have decided to start with a very simple example, and I'm going to work on the isolated system. So what I want is, I want to prepare an isolated system containing 1 mole of an ideal gas. So this is how I'm going to do it. I'm going to take first the ideal gas in a stainless steel cylinder. Do you think in this way the gas is isolated? If I put this stainless steel cylinder in air, then what will happen? The stainless steel walls of the system, they are conducting. They will be able to exchange thermal energy with the surrounding air. So this is by definition not an isolated system. An isolated system is one where the system does not interact with its surrounding. So now I'll have to do something more to this setup to make it an isolated system. And this change will be made at the wall. So let me add a layer of insulation to this wall. And now, as I understand, the gas molecules are present over here. We cannot see these gas molecules with our naked eyes, but they are there. I can weigh the gas cylinder before and after putting the gas in it and find out the number of molecules of gas which are present in the cylinder. Now, after I have made this isolated system, then I understand that this gas molecules or the gas contained within the cylinder is now surrounded by a wall which is rigid, which is non-conducting because I have put in this layer of insulation as shown here, and therefore I would say that I have an isolated system. Do you think the particles can move out from inside the cylinder to outside? The answer is no. So, the gas molecules will be confined within this cylinder. Now, when I go ahead and look at further the properties of this gas cylinder, then I find that my system of interest is now surrounded by a wall which is adiabatic, which means that it is insulated and therefore it does not allow any exchange of energy between the system and its surrounding. The wall is rigid. This means that the volume of the gas will remain unchanged all throughout the time that I have kept it in observation. So, volume is independent of time. Moreover, the stainless steel cylinder doesn't have any gaps or holes in it, and therefore it will not allow the passage of any matter across the wall between the system and the surrounding, and therefore the wall is impermeable to the gas molecules contained within the cylinder. So, under such condition, I would say that I have prepared the system of 1 mole of an ideal gas that cannot exchange energy, volume or matter with its surrounding. And therefore, all the properties of this system will remain what it is if I go on making any kind of observation on this? If I leave this cylinder on the table in the laboratory, will you see any change, any gas coming out? The answer is no. All the gas molecules will still be there inside the cylinder. Therefore, I would say that when I have prepared an isolated system, the system has a constant value of volume, a constant number of constituent particles, and in addition, it has a constant value of energy. This is the basic concept that was introduced by the first law of thermodynamics. It said that in an isolated system, the system is not interacting with the surrounding. Therefore, its net energy content is going to be independent of time. Therefore, I can characterize the equilibrium state of the system by specifying that, okay, U, its internal energy, has some kind of a constant value. V, the volume of the gas, it also has some kind of a constant value. And the number of particles, they are also constant. And that gives you the fact that the equilibrium state of this system can be defined by specifying the value of U, V, and N. So, in an isolated system, you require only three variables U, V, N and their specific values to define the equilibrium state. And therefore, I can say that there are only three variables that I needed to do this definition. But you can obviously ask me that what happens if I have a mixture of gases inside that cylinder? In that case, what I will say is I will use, instead of one single number n, I am going to use numbers of each species like n1, n2 and n3 etc. such that n would be equal to n1 plus n2 and so on and so forth. Since none of the species will be leaving the system, therefore I understand n1 will be a constant, it would be independent of time, n2 will be a constant independent of time, and therefore once again the total number of particles present in the system will also be independent of time. Now, if I have not an isolated system, but what I mean as a closed system, then what I would do is the same cylinder that I had before, a stainless steel cylinder with the gas inside it, I will put it in contact with what I know as a thermostat. So, what is a thermostat? In the laboratory, what you will do is you will take a very big trough or a very big pan, fill it with, let us say, hot water, and you attach a thermometer to it, and you take your stainless steel cylinder and put it inside this thermostat. Then what would happen? You will initially, if you feed another thermometer over here, you will see that the recording of this thermometer is going to change, and there will be small changes in this thermometer as well. But after some time, what will happen is the recording of the temperature of the gas is going to become equal to the temperature of the thermostat. So, in this case, it's very important to note that now the system, 1 mole of an ideal gas, is separated from its surrounding, which is constituted by this thermostat, by this particular wall, which has been shown in green. And here I find that this wall is diathermal, rigid and impermeable to the gas. Now, please note that unlike the isolated system, the wall is now diathermal. That is because I have stripped out the insulated layer. So the wall is made up of stainless steel only, which is a metal. It is a good conductor of heat, and therefore now heat can flow across the wall from the system to the surrounding or from the surrounding to the system. And therefore, I can say that this is how the exchange of different quantities would look like in a system like this. So now energy can be exchanged between my system and the surrounding constituted by the thermostat, but no volume will change and there will be no exchange of matter. Therefore, when the system attains equilibrium, what I would get? The system will be characterized by a constant value of the temperature, which is equal to the temperature of the thermostat. There will be a constant volume of the gas, and there will be a constant number of particles simply because the stainless steel wall without holes is still impermeable to the gas. So under such condition, I will define the equilibrium state of the system in terms of these three variables: the temperature, volume, and the number of particles. Now I can have another type of closed system where I allow not only exchange of energy but also exchange of volume. So in that case, the wall needs to be diathermal, then it has to be flexible or movable, but it can still be impermeable to the gas such that it satisfies the requirement of a closed system that the total number of particles within the system will remain constant all throughout. Now, how do I prepare a system like this? So, unlike the previous case where I have this stainless steel jar within which my gas molecules are present, I would attach here on one side a movable piston, which is in an ideal case frictionless and massless. And then I will put on the top of the piston some kind of a weight and attach to it a barometer so that I can directly measure the pressure that is being exerted on the gas by this wall. In such a condition, the wall surrounding my gas is diathermal, flexible or movable at least in one direction, and it is impermeable to the gas. So under this condition, what I understand is my system can exchange energy and volume with the surrounding, but it cannot exchange any matter. And therefore, the equilibrium state will be characterized by a constant value of temperature, constant value of pressure, and constant number of particles. And I would say then the equilibrium state of this system will be characterized in terms of three variables like T, P, and N. So this way, different experimental conditions can be represented in terms of three variables and three variables only. Now comes the question of an open system. So with the setup that we are using now, how do I create an open system? I punch some holes on the wall of the stainless steel jar. Okay, this would say that the gas can escape from within the system to outside, and therefore by definition here the number of particles in this system is not a constant, and we label such systems as open systems. And in this case therefore the wall is diathermal, rigid and permeable to the gas. And in this case the system at equilibrium has a constant temperature, constant volume, and the third set of variable which is a new variable. It is no longer the number of particles, but rather it is chemical potential. So it is an intensive variable just like temperature, and let us say that this is called the chemical potential mu. So under the condition when the system can exchange both matter and energy with the surroundings, the equilibrium state of the system is characterized by temperature, volume, and chemical potential. The next idea is that once you have defined the equilibrium of the system with its surroundings, then comes the question of how to understand the passage of the system from one set of equilibrium state into other. So, if you want to understand the change in state in the laboratory, you will have to handle a situation like this. You have an initial equilibrium state, which you have defined in this case, for example, at temperature T, volume V, and the number of particles N. Then you will have to perturb the system. And when you perturb the system, for example, you can heat the system and then allow the system to reach a final equilibrium state. So after some time, you will find the reading of this thermometer has attained a value which is independent of time. So that is another equilibrium state, and this equilibrium state will be characterized by some other value T prime of the temperature of the system, volume V, and the number of particles N. And there can be different ways in which this change of states can be carried out, leading to different types of equilibrium states. The first one is a well-known thermal equilibrium, which is established when you take one system at high temperature and you put it in contact with another system at low temperature, and you separate the two by a diathermal wall so that they can exchange energy with each other. What will happen then? Energy will flow from the region of high temperature and low temperature, and the final equilibrium state will be established when the temperatures in both the compartments are equal. You can have a mechanical equilibrium. So in that case, you actually put a system where the gas is maintained at a high pressure in contact with a system where the gas is present at a low pressure, and the intervening wall is made up as a movable wall. So what will happen? The gas at high pressure will push this wall to the direction where the pressure is low, and the final equilibrium state will be established when the pressure is equal in the two compartments on the two sides of the movable piston. So similarly, one can talk about putting two gas compartments in contact with each other, where the first one is present at a high temperature and high concentration of the gas, and another compartment which is at a low temperature and a low concentration of the gas. If now these two compartments are separated by a diathermal wall which has several pores in it for matter flow, what will happen? Matter will flow from the region of high concentration to low concentration, and heat will also flow from the region of high temperature to low temperature. So when will the final equilibrium state reach? It will be reached when there is equal temperature in both the compartments and also an equal chemical potential in the two compartments. So these are the ideas about how we define equilibrium condition in a system which is in contact with a reservoir. For example, if you have put it in contact with a thermostat, we would say that the system is in contact with a thermal reservoir. In that case, the thermodynamic state of the system in the initial and the final state would be characterized by combination of temperature, volume and number of particles, and the condition of equilibrium between the system and the thermostat is that the temperature of the system is equal to the temperature of the reservoir. Similarly, if you put the system in contact with a thermostat and a barostat, which is nothing but a pressure reservoir, then you would find it convenient to define the equilibrium state in terms of temperature, pressure and number of particles. And in that case, you will see the final equilibrium state is established when the temperature and pressure of the system is equal to the temperature and the pressure of the reservoir respectively. I will stop this lecture here with the summary that we have talked about what equilibrium states mean in a macroscopic system. So you can have an initial equilibrium state, you can prepare the system in this equilibrium state. Then you will have to perturb the system and induce the system to undergo a change in state. When the system undergoes a change in state, it eventually terminates into another equilibrium state. And we ask the question that under different experimental conditions, how do I know that when the final equilibrium state is reached? We would say that if I measure properties like the temperature and pressure of the reservoir and the system, and when these properties become the same, we would say that the new equilibrium state has been established. We will discuss more about all these in the next class. Thank you.